Hello to the presentation explaining neural networks. So far in the workshop, you learn about linear regression. In this presentation, we will show you a simplistic explanation of how neural networks work. My name is Ludmil Pelov, and I work as a solution architect at the Oracle A team, responsible for architecting, design, and review for strategic customers. I specialize in chatbots, data science, machine learning engineering. So why neural networks and what are the advantages of the neural networks? Often we have problems that require nonlinear hypothesis learning, or the problems are complex and have a complex relationship that it's not easy to be fitted and expressed into a linear model. In many cases, also we need some algorithm that is less sensitive for different feature distributions. And of course, something that can work in parallel better than other algorithms. Specifically, neural networks actually came originally from the try to mimic the human brains, and they were actually widely used in the 18th, but diminished in 19th, and seen some big renaissance lately, also due to increase of the computational power and GPU capabilities. A lot about neural networks will be explained in the context of the exercise. In the exercise, we will use images of handwritten characters with known labels. We will use those labels to fit a regular neural network and make it learn to recognize these images. On the end, we will test how well the newly trained neural networks perform on dataset that the neural network has not seen yet. So what is a neural network representation? Very often you see something like this, where you have something at the beginning, something in the middle, and something on the right side. So on the left side, it's what is called input layer. This is the layer that it's taking the initial information that's going to be used to feed through the neural network and try to learn. In the middle are the hidden layers, or how some people refer as a magic, where actually the learning is happening. And we have an output layer that, depending on what problem you try to solve, could have one or many neurons as well, which will, for example, in our case, be used for the classification to be able to identify if a digit number, handwritten digit number is 0, 1, 2, 3, or and so on up to 9. So how the neural networks actually learn, and the basic of the learning process of the neural network is what is called forward and back propagation. The input layer, which we feed it with our image information, will be used to do a forward propagation. For the forward propagation, we are going to seed all the links between the input layer and the hidden layers with weights, and all these weights will be actually randomly selected. Once we did the forward propagation and it reached the output layer, we're going to calculate the error, which will tell us how far we are from the result we want to achieve. Depending on that, we are going to proceed with what is called backpropagation. And the backpropagation is the process that will allow us to adjust the weights so that we minimize the error in the output layer and be able to learn the handwritten digits. So let's see how we can calculate, for example, this first neuron A1 on the top. So for this neuron, all the input layers will be connected to it. And with these connections will be actually given a weights. Weight 1, weight 2, weight 3, and so on, depending on the number. In our case, since we have a 28 by 28 image, this is going to be a 724 weights, which will be randomly selected. All these weights will be calculated with the first input layer. Basically, what's going to happen is that every neuron from the first layer will be multiplied by the given weight, and we'll get the sum of all these multiplications. Now, for the neural network to be able to learn, what we also going to do is we need to scale the first layer. So when we feed the first layer into the neural network, we are going to make sure that the values are something between 0.01 and 0.99. On top of that, the weights, which are going to be given to the neural network randomly, actually will be within the same range as well. To make sure that this first neuron, after we do the calculation, we get the sum of the multiplications of all these input neurons and weights, it's also something that it fits between 0 and 1. We're going to use a so-called sigmoid function. Sigmoid function is also called activation function. Could be several different types of activation functions, but they have the same purpose. The difference is that some of them are computationally quicker, and like the rectify function, for example, find a more use today because it requires less computational power. Now, once we do this with the first neuron, this calculation will be done with all other neurons in the first hidden layer. This is not done step by step, by the way, and it's done by what is called vectorization. With the vectorization, allow us actually to do all this calculation in one pass, and we don't have to wait for the calculation of the A1 neuron, then for A2, A3, and so forth, but we can do the calculation of the neurons in the first hidden layer in one pass. Once we've done this with the first hidden layer, we're going to jump to the second hidden layer, and we're going to do the same calculation again. Here we have A1 but in the second layer, and how we do this calculation exactly the same way like we did with the first hidden layer, with the difference that now we use the neurons from the first hidden layer. We pass some randomly selected initialized weights and use the sigmoid function again to be able to calculate the values. As I said, in the forward pass, very important, the weights are actually randomly selected. So on the end, we have the output layer. So when we calculate the first hidden layer, the second hidden layer, we go to the output layer. The output layer and the calculation of every one of these 10 output neurons is done actually exactly by the same way. We get the calculated neurons in the second hidden layer, populate some randomly selected weights, use the sigmoid function to calculate the output neurons. The difference with the output neurons, however, is that every neuron will have a specific meaning. So the first one, for example, will account for the number 0, the second one for the number 1, let's say the third one for number 3, and so on until number 9. So the output layer is going to be responsible for the final decision taking, and each neuron will represent one of these numbers. So what this representation actually really mean? Well, it's going to be a vector with zeros, and depending on where we have an activation, we're going to have a number very close to 1. It's not going to be actually 1, but it's going to be something like 0.99, 0.95, or 96. The higher it means that the more likely is that the number we see here at the top, for example, is the number 0 we want to learn. If the second neuron is activated and we have there the highest value, then this means then in our case that we learned that this is, or with the neural networks considering this to be the number 1, and so on. So how to fit the weights to make sure that after we've done this forward passing and we did all these calculations, the outputs we have there are correct, which is not going to be to happen on the first pass. So this is where we use the backpropagation, and the backpropagation basically will go and do the same steps back to the neural network And we'll try to update the weights in a network so that the actual outputs in this vector where we see the 1 and the zeros get closer to the target output. And we do have the target outputs because these are label data. We know when we feed number 1, number 0, and so on to the neural network. This is also called a supervised learning because the information we feed to the neural, we know the answer, and we would like to make the neural network to learn that answer as close as possible. There are a lot of mathematics involved, but at the intuitive level, you could say that during training, it will adapt the weights in such a way that the resulting predictions match the labels as closely as possible. This weights adaptation will be done for the weights between the output layer and the second hidden layer, as well between the second hidden layer and the first hidden layer. On the end, when a model is built, the model will be nothing but all the weights calculated during the process of learning in the neural network. Additionally, to additional terms to be able to know and important to know during the work with the neural networks are, for example, epoch, which is the number of times the neural network runs through all the training examples. And batch and epoch actually are important to know together because in many cases, the training set is going to be very big to be able to fit in one pass. Maybe you don't have that much resources, so the training set is so big that cannot fit in a memory, in a GPU memory, on your computer memory. For that reason, what we do is we specify a batch, which is the size of the amount of data you want to run through the first pass. And this is just a subset of the entire big data set. So once this batch has run, the weights are going to be updated. Then a second batch is going to run, and then the update is going to be updated, and so on until the neural network's seen all the data. Once all the data has been seen, this is what's called one epoch. So if we specify that actually our neural network has to run 10 epochs, this means that actually we want our neural network to see the entire data set 10 times. We have also what is called the loss function, or this is basically the cost function that is showing how much of our output layer is from the desired output or the labels information we have in the training set. Activations. This is the activation for the single neurons, and this could be, sigmoid in our case, could be also ReLU, softmax, and so on. Optimizer is used to adjust the weights or to minimize the objective and the loss and the error function. Basically, this is what is used to get the partial, to run down to the partial derivative and see if there is actually optimization. This is your optimization objective. And the metrics you see also in your, some of the neural networks are used to monitor the performance of the model. It's like the loss function, but not resulting in something that actually it's used during the optimization process. I hope that this has given you some idea of how neural networks function. In the exercise, there are more points for you to understand them. Good luck with the exercise.